Kathleen Lonsdale was known to be a very hard-working chemist.
It was absolutely groundbreaking, which was hugely impressive.
It's really amazing how you could solve this 100-year mystery by hand at home.
I suppose most of you have seen a crystal at one time or another. All matter is made of atoms. In crystalline matter, the atoms are arranged in regular order. The idea is that the crystal is a pattern of atoms, a regularly repeated pattern of atoms, like the regularly repeated pattern of a wallpaper.
People had been studying the external form of crystals for an awful long time. I mean, they are, I'll just show you this because I think, crystals are beautiful. My name's Judith Howard. I'm a retired professor of chemistry at the University of Durham. My specialty when I was full-time working was X-ray crystallography. So people looked at the external form of crystals and they didn't, how do you know what's in it? To all intents and purposes, when they were studying the external form of crystals, they might as well be looking at a block of wood like that. They couldn't see inside it. You can't see inside a crystal because the wavelength of natural light does not match with the separation of the atoms. If we're talking about something as simple as that molecule, let's say, it's something I worked on, what we're looking at here is not much more than an angstrom between that black atom and that black atom. You need to use radiation or incident radiation on the crystal, which is commensurate with the interatomic distances. That doesn't work with white light. They discovered this new unknown radiation by Röntgen in 1895. It was called X because it was unknown.
X-rays are very fine waves indeed, far shorter than light, and by seeing how bodies scatter X-rays, one can argue back to the way the atoms are arranged in these bodies. We do it by means of a crystal structure. And so I'll put crystal structure there, and I'll put X-rays for examining the crystal structure, and say that with these X-rays we can actually see how the atoms in the body are arranged.
So X-ray diffraction then and now is a method of determining the molecular and atomic structure that was within the sample you used to shine the beam on. We were working with very tiny crystals, and one actually positions these small crystals in an X-ray beam. They diffract from the atomic contents of the structure, and then you catch those beams on either a photographic plate, which is what we used to do. Now, of course, it's electronically. So those would be the sort of diffraction patterns we would be able to record on a photographic plate. And even if you don't get much from these pictures, you can see that they are different, and you can also see that in some of them the intensity of the spots varies quite a lot. From the pattern of the spots and the intensity, we can work backwards to what was actually inside these tiny crystals, which of course is what Kathleen was trying to do.
So Kathleen Lonsdale was actually working here, right here at the Royal Institution when she was working for the Braggs. And that was when she first came into the field of X-ray crystallography. Well, my name is Judy Wu. I'm a professor at the University of Houston. I'm a computational organic chemist, and so in my group we do a lot of research on the topic of aromaticity, benzene and benzene-like compounds.
And it was a very, very new subject when Kathleen was doing this work. I mean, the Braggs did their work in about 1912. I think the Nobel was 1915 for the younger Bragg. And Kathleen was doing this work in the early 20s, so it's really very soon after the people were working on how on earth they could use this new radiation. It's quite a big leap.
I've actually known that Kay Lonsdale resolved the X-ray crystal structure of benzene during my graduate student times, but For the longest time, I thought K was the initial of a man, and I didn't realize that it was for Kathleen until much later. So benzene is a small 6-membered ring organic molecule, and it's actually one of the first, not the first, but one of the first aromatic compounds to be isolated. So Michael Faraday isolated benzene on June 16, 1825. This was a time when chemists thought that chemical composition, so how many of what type of atoms are in a molecule, was all there is to know about any pure substance. And so when Faraday announced the bicarbonate of hydrogen, later known as benzene, 6 carbons, 6 hydrogens in a ring, for the longest time, this is what chemists thought that was all there is to know. When it occurred to chemists that structures started to matter, that was a brand new topic for chemists. And so many different chemists tried to come up with different structures of benzene. And at this time, a chemist named Auguste Kekulé came up with the structure of benzene, showing that the 6 carbons could be in a ring. And this was inspired by a dream that he had about a snake biting its own tail. And so this was really new thoughts and new concepts of the time. And of course, the single and double alternating bond of benzene still was not a perfect structure, that it didn't explain all the chemistry observations of benzene, but it was a very good start. And throughout the 19th century, actually, research around benzene and benzene-like molecules actually pushed forward a lot of industrial revolutions, and that included the coal tar dye industry, the petroleum industry, and actually later in the 20th century, the medicinal chemistry. And with all that development came a lot of new chemical knowledge that formed the basis of what we teach in organic chemistry textbook today.
Why? Look at the benzene ring. That is the grouping of the carbon atoms in rings of 6, which is a fundamental feature of organic chemistry.
So even though Kekulé came up with a pretty good model for what the structure of benzene should look like, there were still a lot of these questions up in the air. And so a lot of chemists tried to come up with alternative structures for benzene. Claus, for example, invented a diagonal bonded structure. Chemists like Ladenburg suggested a prismane structure for benzene. Armstrong showed little arrows pointing from each of the carbons towards the center of the ring. Thiele drew a dotted circle around the benzene ring, showing that the idea that each of the carbon-carbon bonds should be equivalent. And Kekulé also later actually revised his model and suggested that if you had a mirror image of 2 Kekulé structures, perhaps the 2 were equivalent and undergoing a fast equilibrium with each other. And so you see, even though a large part of these models were all done during the pre-electron period, and so all of these questions were still up in the air. Was benzene planar? Did it have alternating single and double bonds, or did it have equalized carbon-carbon bonds around the ring? If it did have double bonds, why did it not react like alkenes and the other less saturated compounds? The puzzle with benzene is actually twofold. It's both about the reactivity, but also about the reaction products. At this time, chemists didn't know about electrons, and they were just coming out from a period of time where they thought that chemical composition was all that mattered. And so the problem of molecular structure was very new to chemists. And so the problem with benzene, first, is that it had a low saturation, so it had a low carbon to hydrogen ratio, like the alkenes and like the alkynes, but it didn't react like the alkenes and the alkynes. It didn't undergo addition reactions, it underwent substitution reactions, and it was found to be relatively unreactive. And so that was the first puzzle. Now the second puzzle was that chemists found that the substitution reactions of benzene always gave less isomers than expected. And so based on the Kekulé's model for benzene, so the Kekulé's model of an alternating single and double bond structure of benzene, you would expect, for example, for a molecule like a disubstituted, ortho-disubstituted benzene, you would expect to have 2 different isomers. One where the where the substituents are connected by a single bond, and one where the substituents are connected by a double bond. But chemists could always only find one kind, and the only way for that to happen is if all 6 carbon-carbon bonds around benzene were equal, and that definitely was not what Kekulé's benzene structure suggested. Chemists are always fundamentally curious about things that don't fit. And I think that's one of the reasons why people were curious about benzene. Second of all, I think this was during a time when the coal tar dye industry expanded, petroleum industry expanded, and so to convert benzene and benzene-like molecules into useful molecules, you had to grow your chemical knowledge. You had to know how to convert benzene into other useful compounds. And so there's both a fundamental reason, but also a practical reason for the interest in benzene and its reactions. So by the time the Bragg and Bragg father and son pair introduced the X-ray spectrometer, it was clear that there could be a solution to solving the structure of benzene. But the solution was not very clear. It was not straightforward because during those times, X-ray crystallography only could be applied to relatively simple structures, so structures like sodium chloride, that's doable. But much more complex organic molecules like benzene, that was very difficult to do. And so what Kathleen Lonsdale did was that she applied a very creative method, a very creative approach to solving the crystal structure of benzene.
She was able to start on this famous problem of hexamethyl benzene because Professor Ingold, who was at Leeds at the time, gave her some crystals, some lovely crystals. She couldn't work on benzene, we can today, but of course then, benzene is a liquid. There was no way of being able to produce the diffraction patterns we would need, ordered diffraction patterns from the liquids in those days. So Catherine would have been able to take some photographs, record some of these patterns, and then of course it was a long process of hand calculations. And just to give some idea, this is a different structure, but each one of those layers has lots of numbers on it. Those are a measure of the relative intensities of the spots, and they're given a number, so you have a scale. So you would be able to measure layers after layers of these. Imagine an OS map, so that the brown contours give you a hill. What one's doing here is trying to look for hills, i.e. the position of the atoms within the crystal that gave you the diffraction pattern. In other words, you're trying to find out the structure. If you get enough of those layers, you can stack them together, and even though you can't see very much, I think you can see that you've got dense patterns, and from those sort of building a model, you can begin to unravel the molecular structure of what was in the crystal.
She realized that when you look at this complicated X-ray diffraction pattern, that pattern can actually be decomposed mathematically through a Fourier decomposition method to give information about electron density, which then gave you information about the positions of the atoms in the crystal. And so she applied this to solve the crystal structure of benzene, and actually for many different organic molecules. And that basically opened doors to solving much more complex crystal structures for chemical compounds, biological structures like DNA, penicillin, vitamin B12, all of that which came later in the 20th century. And so it really changed the landscape of solid-state chemistry.
That was the first structure which unequivocally demonstrated that benzene, the shape of benzene, and the fact it was flat. And this was all done by hand calculations, which was hugely impressive. There she was able to use a technique called Fourier analysis, and that was enabled really by her brilliant mathematical mind, because she'd been working on the way in which you could interpret the intensities that we get on the photographic plate to work back to what the space group might be, and that's a question of symmetry. She worked with a fellow student at the time, or researcher, Asprey, and they together worked out these mathematical formulae for the summation of the intensities for the 230 space groups that we use in crystallography. And from there they went on to produce what is now known as the international tables. The first set of these, which is hand-drawn, and I have facsimiles here, hand-drawn by Kathleen, was published in 1931. A major work was, as I say, this mathematical, producing these tables that then people could use. Sometimes it's hard enough to use these tables to understand what there is on the page, let alone actually to have developed the mathematics to do it. So that was very generous. But the formula in the middle there will give you the summation of the various intensities to then allow you to go forward and produce maps and begin to build the model of the chemical species you're looking at, and thence to produce pictures such as that. I mean, it looks very fuzzy by today's artistic work, but it was absolutely groundbreaking.
Well, Kathleen Lonsdale's work really proved that benzene was flat and was a perfect hexagon. That solved all the answers that chemists had about benzene structure. I think also is interesting is that when she was solving the time that she published the 2 papers on the structure of benzene, that was actually during the time that she was at home and taking care of her children. She had no access to a lab or any equipment. And so she was solving all of that by hand at home. And here comes the 2 very important papers solving this long-standing mystery of the structure of benzene.
I tried to demonstrate some of the ways in which she would have had to work in those days. But today, and even when I started my DPhil, a chemical crystallographer working for a PhD would probably manage to solve 3 simple to medium complex structures in a 3-year PhD. 3 structures in 3 years. Sometimes not even that, depending what complexity. I mean, we can do 3 before breakfast. I mean, 23 by lunch. I mean, it's changed dramatically because we're using much stronger X-ray beams. We're using much faster detectors. We're using super fast computers. It's all been moving on together. And one development leads to another. And Kathleen would be delighted, I'm sure, but amazed at what can be done now in an ordinary chemistry lab. In a way, it all ties in together because she's a very brilliant person and a bright mind and very focused, very determined to find answers.
I do think she should have won a Nobel Prize, and I think the fact that she didn't was more about her time than about her work. Her work basically formed the basis of how modern X-ray crystallography is done today, and because of her work, it opened doors to enabling chemical structures, organic structures, and biochemical structures to be resolved by X-ray, and that really is a cross-disciplinary influence.